Hey, welcome back. Week 3, we're going to talk about Paleozoic, Mesozoic, and Cenozoic paleogeography of our southwestern U.S. region. Hey, check out that image, huh? Look at that dinosaur party going on. Woo! Volcanoes erupting in the background, dinosaurs frolicking everywhere. I mean, little, big, the works. What I draw your attention to is, besides the rock climbing dinosaurs, is look at the vegetation. Tropical ferns, water flowing through there. In these sorts of reconstructions, how do geologists figure out what the landscape looked like? What was the climate, right? And of course, we do it by looking at the rocks. So in any picture you see of sort of Mesozoic type dinosaur land, you'll see rivers, you'll see tropic trees, all these kinds of things. And there's a good reason for that. And again, the rocks we find tell us that that was the climate. So our objectives this week: define what paleogeography is, then briefly show how it's determined and utilized, and then finally describe the general paleogeographic record for the western U.S. from the Paleozoic up to the recent. It's going to be brief. So paleogeography is the study of historical geography, basically, where we're looking at the ancient distribution of environments. Now, again, you know that there's various types of depositional environments. You can break them into marine or non-marine. And of course, there's lots of different marine environments. You can have limestone forming, or you can have deep water sediment fans. You can have lakes on the continent. You can have rivers, deserts, beaches, hot or cold. So how do we tell the difference of these things? Well, by looking at the rocks. And I'll give you a couple of examples. Here on the left is a beautiful shot of the bottom of the Grand Canyon. And what you're seeing is these are the Cambrian layers here. The Cambrian, and then it goes up to the sort of Devonian. And then these steepest, reddest cliffs in the Grand Canyon is called the Red Wall Limestone, and that's Mississippian in age. And if we look over here to one of these typical paleogeographic reconstructions, we'll see that I've put a red ellipse in here, and this is the area of the Grand Canyon region during that early Mississippian time period. So what you're seeing is that light blue represents shallow marine waters where you're collecting a lime residue or precipitate, and this is, coral reef type of thing. And then as you move to the west, we get deeper and deeper, and the waters get a little bluer, and then out here you see the deepest, bluest part of the ocean. So this is shallow, this is marine, this is warm and full of the ability to make limestone. Something like the Bahamas today, that kind of environment. Well, simultaneously, we see that okay, if you were in Arizona, Utah at the time, you would be in this shallow marine water, and what we're going to find all around this region, anywhere you see light blue on the right image there, you're going to see limestones. But same diagram, when we go to the west, right, to the left here, to the west, we see that there is a proposed, or at least they suggest, some sort of mountain range. And notice that mountain range is offshore, right, separated here. And the proof of this, or at least the evidence of this, are these rocks in central Nevada near an area called Carlin. And there's a famous gold mine near Carlin. Anyway, what we see in Carlin is a Mississippian aged angular unconformity. These are older Paleozoic rocks, and then there's an angular unconformity with younger Mississippian rocks, and later than Mississippian on top. So this is a Mississippian aged angular unconformity, and that is the evidence that there was some type of mountain building going on in the west. And in fact, this is called the antler orogeny. This is one of the first orogenies recognized after this area. It's a passive margin most everywhere else, but there is this evidence of a strip, a region of higher, more mountainous, and the proof of that is this angular unconformity in these rocks. So that's how this is done, right? You just basically go everywhere, look for rocks, what do they tell you, and then you can reconstruct the environments. So we said that it's the study of historical geography, and paleogeography has been crucial to the geosciences in just a variety of contexts. Number one is when you look at sedimentary basins and you're able to track what's going on in that basin at any time, and again, this is by zooming in and really taking a good close look at what those seds are doing, then you're going to see that that plays a big role in the field of petroleum geology. So if you take some classes at UAA in petroleum geology, you're going to do a lot with the paleogeography. What types of environments were where and when, and that all has a big factor in where the oil would be. Another way that paleogeographers have really helped out the geosciences is that they look at what are the sedimentary environments that are associated with fossils. And so it's not just enough to find a fossil, but if you're like, okay, this fossil lived in this type of environment, it really gives you a good clue to what kind of, what was that species all about. And so, if you can say, oh, well, this was a warm, beach. And so anyway, that really helps to understand what's going on there. And then paleogeographic evidence was absolutely critical in the development of the continental drift theory, because where the beaches were, where the offshore shallow areas were, this is what defined these old continents. And so if you can look at oceans and continents, you can put this all sort of back together again, because of course things were different. So reconstructing supercontinents like Pangaea or these ancient oceans requires a knowledge of sort of peeling back the layers and going back in time to what these continents would have looked like. So paleogeography, a big deal in the geology world. And if you're going to understand paleogeography, one of the key principles was put forth by a guy named Walther. And Walther's principle basically says that the vertical and the horizontal facies, they have to match. Now, I've stolen that text and put it in there for you word for word, but here's how this works, right? So it says the various deposits of the same facies area. So like the shale facies here, or the sandstone facies, or the limestone facies. The similar sum of the same facies areas, and similarly the sum of the rocks of different facies areas, are formed beside each other in space. That means that you don't find sandstone right next to limestone. You always find sandstone next to shale, which is then next to limestone. And if you find them lying next to each other in the modern environment, then what we can do is find them lying on top of each other or on the bottom of each other in the rock record. So it's common to find sand next to mud. Therefore, we should find sandstone next to shale in the rock record. That's okay. It says with biotypes, it is a basic statement as far-reaching significance that only those facies and facies areas can be superimposed primarily, which can be observed beside each other at the present time. That's a fancy way of saying that if the depositional environments don't meet in the modern world, then we can't have those layers next to each other in a stratigraphic section. Over on the right, the cartoon here shows various depositional environments where we would find various species of trilobite back in the Devonian. So you can see that there's an outer shelf, which is a special type of shale, this graptolitic shale. Then it grades into a gray micrite, then to a biosparite, a carbonate mound, and then finally into the nearshore clastics like mud, like sand. So all of these, right, are limestone. So it's limestone, shales, and basically sands, just like you're seeing here, just broken down even further. Still confused? Well, if we take a look, so it said the various deposits of the same facies area, and similarly the sum of the rocks of different facies areas are formed beside each other in space, though in a cross section we see them lying on top of each other. All right, so here we go. Limestone, shale, sandstone. The kind of sequence that you would find if you took historical geology. This would be a transgressive or a regressive sequence depending upon the order they're in. So when we go to the bottom of the Grand Canyon, in the Paleozoic, the very bottom of the Paleozoic Cambrian time period, we see the Tapete sandstone, the Bright Angel shale, and the Moave limestone. All three of those are conformable with each other, telling us that the sandstone, the shale, and the limestone form next to each other in the rock record. That means everything's good to go. And then here's an actual picture of these units. The steep unit here is the Moave limestone. The slope former here is the Bright Angel shale, and then this little unit here, the thin unit here, that's the Tapete sandstone. Now below the Tapetes are these older Precambrian sediments in the Grand Canyon. So when you're doing paleogeography, you're looking for units that belong together, that belong next to each other, okay? And you guys know this because when we cruise around the planet and you take a look at depositional environments, right? I say here that we know that conformable layers reflect adjacent depositional environments. So if we look over a wide geographic area for rocks of the same age, we can see the extent of different ancient environments, and that's paleogeography. So this is going to be a limestone somewhere, this is going to be a beach, this is going to be coal or a river deposit, right? And when you put them all together, this is what we're looking for, is to reconstruct what did it look like at any one time slice, and we do that by looking at the rocks. Now, if we have two rocks that don't match up, right? Like let's say you've got limestone next to a playa lake from the desert. Maybe there's an unconformity. Maybe there wasn't something deposited, maybe there was something eroded, that sort of thing. So that allows us to identify time breaks if we see two non-correlative units next to each other. Well, just to give you a reminder, because we're about to talk about geologic time, this is the simplest time scale I can make for you, which has been reduced down and covers all the basic stuff you need to know about the western United States. So again, we're not talking about the Precambrian, right? Precambrian rocks, they're laying there. Okay, so here's the Cambrian, and I tell you that there's limestone, shale, and sandstone deposited. That's our transgressive sequence in the Cambrian. That's when the seas come onto our passive margin. That's a transgression. Then in the Ordovician and Silurian, we're going to see there's a disconformity in the rock record. Basically, these layers are not present in the Grand Canyon, which means that either they were deposited and eroded away, or they were never deposited. Then from the Devonian, right, Mississippian, Pennsylvanian, and Permian, it's going to be deposition in that Grand Canyon region. We'll talk about the Mesozoic, the Triassic, the Jurassic, and Cretaceous, and then we'll come on up into the Cenozoic. This is a great diagram. If you haven't printed it out, you should, right? This is the thing that you got to keep in mind. All the basic activities going on one simple diagram. Okay, so let's get going. Now I'm going to show you snapshots in time, not every one, but from the Paleozoic on up. And if you want more details on the southwestern US or anywhere else, you just got to Google it, right? You'll find many of these diagrams for the paleogeography in any area you're interested in. Now the ones I'm using are from Northern Arizona University, and there's a guy there that spent a lot of time working on this named Ron Blakely. Anyway, he's got these beautiful reconstructions in high resolution that you can go have a look at. Okay, so like we said, for most of the Paleozoic, in the regions we're interested in, it's going to be marine deposition with just a few exceptions. So over here on the left, you can see this is the Middle Cambrian. So now in the Middle Cambrian, the seas have advanced onto the continent in the area, again, because there's Nevada, there's Utah, there's Arizona, there's the Grand Canyon region, right, Nevada. Now remember, the edge of the continent is right over here. This the whatever was here, this side, went further west in the rifting event during the Precambrian. So this is our continent. Light gray, shallow marine waters, and of course, this is actual continent. So let's say you were in the Middle Cambrian and you were looking in New Mexico, you would see non-marine deposition. But, and again, where we're going to be, it's marine. So these are those bottommost layers in the Grand Canyon. By the time we come up into the middle Ordovician, right, it goes Cambrian, then Ordovician, look at what they reconstruct for the region of Arizona, right? It's land. And that's why you don't see any units in the Grand Canyon, because this particular time frame there was either a lack of deposition or these rocks that got deposited were pushed up somehow and then eroded away, because we're not going to see any rocks until the Devonian. So small land masses like that were popping up here and there, but for the most part, all over the West, it's just simple deposition, marine deposition in the areas we're concerned with there, Arizona and Utah. Now, this is the late Devonian, and again, it's different, you know, marine depths in Nevada. This is mostly going to be limestone, and again, there's sands that filter in muds here and there, but for the most part, it's just going to be a big, thick stack of limestones. I'll show you these in all their glory when we drive through a place called the Virgin River Gorge. Now, over here in the early Mississippian, and this is the diagram I showed you earlier on in the lecture, what we see is, again, throughout the Grand Canyon region, we see this shallow marine shelf where we're getting a lot of limestone deposition, forming the red-walled limestone in the Grand Canyon. And that continues all the way across Nevada till about the central part of Nevada, and then western Nevada is this antler mountains from the antler orogeny pushing them up. That's going to create sands, muds, river deposits over there. Now, by the time we've made it up into the early Pennsylvanian, right, because it goes Pennsylvanian and then finally Permian, we see that there's quite a few more land masses scattered around the west. You're going to see that at times in the Grand Canyon, where the Grand Canyon would be, is it's not all limestone, it's sands. We're going to see sandstones, windblown sands. We're going to see muds, all right, up there at the higher levels of the Grand Canyon. In the Permian in the Grand Canyon, that's the very rim, right? That's the rim of the Grand Canyon, is the Permian Kaibab limestone that extends all over the region. And that's the last time. That's important because that's about the last time you're going to see the sea in any extent, wide extent, over the western U.S. So again, they're showing here in the late Permian that the sea has already receded, right, further to the west. And notice that the mountain ranges are getting quite a bit more extensive. This is, again, antler orogeny going on over here. Okay, so then we get into the Mesozoic. Rim of the Grand Canyon is the top of the Paleozoic, and that is mostly marine, and then that's it. The sea recedes, and we don't see the sea in here again. There is stuff deposited in water, because you're going to see, like up here in the corner, you're going to see these small inland seas, you know, more freshwater stuff, but you're not going to see the ocean in there in any great extent. So non-marine sedimentation is going to take over, and we're going to see a lot of rivers, at least at first. So here in the Triassic, you see that they give you lots of lowlands coming out of these small highlands scattered about. But there's a lot of sand and mud, so we're going to see a lot of rivers with sandy and muddy. This is the classic sort of territory for the three-toed dinosaurs that you see stomping around the west. So it's an area that I'll guess wouldn't look unlike some of the southern U.S., Louisiana, that kind of situation. Anyway, over here in the Jurassic now, in the area we're concerned with down here in Utah, Arizona, in the Jurassic, this is all going to be a huge area of sand dunes. It's a deepening sedimentary basin that's in the front of this ever-growing orogeny that's been well developed by the Jurassic time period. So we've got a large set of mountains, again, because all of this is arc, right? This is subduction zone and arc. There's volcanoes, right, over here. Anyway, in front of one of these convergent margins, you're going to see, at least behind it, in front, you're going to see a similar situation as you do in Alaska today, with a trench and a forearc and volcanoes. But in the back arc, behind the arc, you're going to see a depositional basin that's going to be really subsiding. And in that subsiding basin, you're going to see a lot of sands and muds. And again, the thick rocks of Zion National Park, the sandstones, right? That's where that sand's being deposited. So let's see, did I cover it all? Right, so instead of platform sedimentation, when you get into the late Jurassic, you're going to see a continental arc to the west with a rapidly developing fold and thrust belt stretching eastward into Nevada and Utah. There is no big folds over here in the eastern part of Utah in the Grand Canyon region, but you do have a deepening sedimentary basin. So large folds along with thrust faults are going to be building this big mountain range as far east as Utah. The Paleozoic carbonate rocks in California and western Nevada now, the ones that were laid down in those early seas, these rocks are getting intensely folded and then intruded by granites of the magmatic arc, which is forming up and down that western North America. So we're going to see those rocks when we head over and look near the Sierra Nevada mountains and also places like Death Valley. All right. So there's a lot of squeezing over here in the west, and this is being the older rocks are being crumpled and intruded and thrust faulted and folded, while over here in the eastern regions, in the early Cretaceous and then the later part of the Cretaceous, these are we'll still see sedimentation. See, notice the difference. Look at this sea. This inland sea is getting ever larger. And then finally, in the area of Zion National Park, you're actually going to see like muds and sands in this Cretaceous period. This is a good time for coals, that kind of thing. It's tropical, shallow water, lots of vegetation. But again, this is a mountain range with large folds and thrusts. So we're going to see a dramatic difference between the rocks in the eastern region to the rocks in the western region when you drive across that area. Well, by the Cenozoic, we've made it out of that large convergent margin, and over here in the area, this is the Cretaceous Tertiary sort of boundary, right? We're getting out of the Mesozoic and we're getting into the Cenozoic, and again, same story, right? Large mountain range in the west, silt, sands, and gravels depositing in the east. By the time we make it into the Oligocene, which is 35 to 30 or so million years ago, what we're going to see scattering and getting ever larger is, see, you can see in here it says volcanics, right? So this is when that subduction zone overruns the spreading center, and along an area that's going to get wider and wider here, and we'll talk about this when we talk about Cenozoic tectonics in a couple of weeks, but anyway, we're going to quit squeezing and we're going to start pulling apart. So up here I tell you that by the Cenozoic there's freshwater limestones forming the rocks of Bryce. After a brief hiatus in mountain building, extension will begin further west. And accompanying the extension are explosive caldera-forming eruptions. These are rhyolites and the like, right, across Nevada. So we're going to start to see large volcanic eruptions burying these early forming normal faults. And these are the last two diagrams. Mid-Miocene 20 to 15, man, this is volcanic hell. All across Nevada here, we're going to see huge caldera-forming eruptions, even into Utah with some of those laccolith type systems. And then over here, this gets up to late Miocene. This is 10 to 5. So this is really getting into the time frame where we're going to see a lot of basaltic volcanism, maybe even those early, very early ash flow tuff systems are shutting down. And things are starting to look, lots of extension here, right? Starting to look like the basin and range. Western North America hasn't quite fallen completely into line with the way you see it today, but again, we only got 5 million years to go. So the final episode, and we'll see this stuff everywhere, is widespread basaltic volcanism. And the basaltic volcanism today is mostly centered on the very margins of the basin and range, both the west, the east, and the south. Pretty cool, huh? Well, hopefully this little geohistory lesson and following those diagrams will help try to help to keep everything in perspective for you. It's not always easy to think about the rocks you find in an area and what they might mean to the bigger picture. But again, if you have a little bit of knowledge, you can think, well, in the Jurassic, I was getting sand over in Zion, and over in the west, in California, there was actually getting granites intruding and volcanoes erupting. So that's pretty different. And what's nice about our field trip is only a couple of days separate from when we're in one place to the other. So in the east, we'll see almost a complete stack of sediments, right? Here's that chunk of that diagram I showed you last week. And there's the bottom of the Paleozoic all the way up to the top of the Cenozoic. And again, those rocks to this day are relatively undisturbed. Again, you have to visit 3 national parks. You have to go to Grand Canyon, and you have to go to Zion, and you have to go to Bryce. But you can see them all. And then showing like the last gasp here is a basaltic volcanism that's punched through everything and erupting on top. Well, in the east, so over in the areas of Death Valley, western Nevada, up near the Sierra Nevada mountain range, we're going to see a very different picture, right? You're going to need to use your information on stratigraphy. You're going to have to think about cross-cutting relationships like those geologic time block diagrams, and you're going to have to think about structural geology in order to work out the various events in geologic time because things are a bit deformed. So here I show you a typical range in the western Death Valley area. And if you take a close look, what you'll see here, and this is a nice photo because it's been kind of annotated for you. But anyway, what you see here, these light-colored rocks are folded Paleozoic rocks. So these are the same age as these rocks over in the Grand Canyon. And remember, they're going to be a little different because they were in deeper water, because they were further west. But anyway, these rocks are intensely folded, right, from those mountain building events during the Mesozoic. Then those rocks get intruded by Mesozoic granites. So the granite comes after, right, the Paleozoic rocks. So we have Paleozoic rocks deposited, then squeezed, then intruded. All right, that's part of the arc that was there. Then Cenozoic basalt is erupted over everything. That's way late in the game. And then that's cut by normal faults. Again, part of the extension. The basalt and the extensional faults are all forming together. Not quite as easy to interpret as this, but no problem for you now since you're getting to be so good at this. Okay, so next week we're going to briefly cover the Mesozoic tectonics of the region, which I've been talking about, since day one. So anyway, it's the story of the development of a active margin where there was once a passive margin. So this diagram shows you lots of the nice features of an active margin, the subduction zone and these forearc sediments being, thrusted in here. This is like Anchorage today, and basins, both forearc and back arc. And this is where we're going to get that fold and thrust belt over here in volcanism. And for those of you that took petrology, look at this, man, we're getting flux melting and some blobs of mafic lavas ponding at the bottom of the crust, and there's crustal anatexis, partial melting, and formation of granites. I can hardly wait. All right, have a great week. Take your quiz. Talk to you later. Bye.